From the previous example, we can see that the gravitational force and the force from the spring are example of what we call the conservative force. The conservative force. The conservative force here means that if you apply the external force to the system, you will give the potential energy to the system, and this potential energy can be changed to the kinetic energy, and vice versa. It means that the kinetic energy can change back to the potential energy. The total mechanical work mechanical work or mechanical energy is conserved. We will discuss this point in more detail in the next chapter, but anyway, it means that we can define the potential energy for this kind of force, and the potential energy can change to the kinetic energy, and the kinetic energy can change to the potential energy for this kind of force. We also have the friction. Which we call it the non-conservative force. The non-conservative force. For a non-conservative force, we cannot define the potential energy. Okay, we cannot define the potential energy for the friction. When we apply the external force to the object under the friction, it will not store the potential energy to the system, but anyway, it will store some kind of internal energy, but it's not a mechanical energy. So the total mechanical energy is not conserved for the non-conservative force. Okay, so this is two kind of forces according to the behavior of the energy. For a conservative force, if you have two property, first, work done by a conservative force is path independent. It's path independent. It means that, for example, if you have an object and you want to lift this object from the initial position to the final position like this. If you apply the external force to lift this object upward like this, or you move it in a curved path like this, we will see that the work done by these two parts are equal. Okay, if I name the first part as the work in the first part as W1 and work in the second part as W2, we must have that W1 is equal to W2, and this is very obvious for the gravitational force. Okay, because the gravity point downward only, so it's not depend on the path you move. It depends on the difference of the vertical position of the object that gives you the external work. Okay. Second property is that work done by a conservative force on an object moving through a closed path is 0. I will not go into the detail of the second property, but it's quite clear if you look, for example, the gravitational force. You can see that the work done when you lift the object to this position is equal in magnitude to the work done when you move it back to the initial position but have the opposite sign. So if you calculate the total work is equal to the work done when you lift the object and work done when you let it go back, and it will equal to 0. To be specific, if we look at the form of the work done by the gravity and the form of the work done by the force from the spring, we will have that for the gravity, we have that the work done by the gravity is equal to the mgyi minus mgyf. Here we use the reference point, and the upward, the vertical upward is a positive direction. So we have that the mg, the work done by the gravitational force, is mgyi minus mgyf. So we have an object at a position yi and it moves to the position yf, and this is the expression for the gravitational work, the work from the gravity. Okay. For the force from the spring, we have that for the force from the spring, we have that the work done by the force from the spring is equal to the half of kx I square minus half of the kxf square. That is, if we have a spring and if the object is initially at the position xi, and then it moves to the position xf, and this is the work done by the force from the spring. Okay, we can see that in both cases the work from the gravity and the work from the force from the spring is not depend on the path, it depends on the initial and the final position of the object, and this also is depend on the initial and the final position of the object. So it has the property of the conservative force, and if you move an object from this point to the final point and then move back to the initial point, the work done by the gravity is 0. And also if you push or you pull the object from the initial point to the final point and then go back to the initial point, you can see that the total work is 0. So these two forces satisfy the condition for the conservative force. Now, if we look back to the definition of the potential energy, we can see that for the gravitational force, Wg is equal to the Ugi minus Ugf, or we can say that this is the minus of the delta Ug. And this is also the same for the force from the spring, is equal to the minus of the U delta Us. In general, we can say that for the internal force or the force of the interaction inside the system, we will have that Wint is equal to the minus of the delta U, or the change of the potential energy.